This is an oscilloscope display of a radio frequency carrier, amplitude modulated by my voice, using conventional AM techniques. Now, by conventional AM, we mean double sideband, unsuppressed carrier amplitude modulation. The important thing to notice here is that when the modulation is removed, the radio frequency carrier remains. Now you're looking at a display of amplitude modulation using single sideband techniques. You notice any difference? The voice variations look very much the same, but when we remove the modulation, or when I stop talking, there is no signal, no carrier. This difference, as you will see, gives single sideband a tremendous advantage over conventional AM. But what is single sideband? For more than 50 years, AM has made voice communications possible over great distances. Literally everyone has made use of it, and the demand on communications frequencies continues to grow. But the frequency spectrum used for communications is limited. Over the years, many types of stations for numerous purposes have come into existence, such as public information and entertainment, public utilities and services, military and transportation, private citizen services, national and international services, and many, many others. And as the population increases, more people have a need to use these services. And you can see what's happening. The frequency spectrum is already too crowded, and getting more so every day. Now, this is a serious problem. So electronic engineers turned their attention to solving it. There were two possible solutions. One, to increase the efficient use of transmitter power so that more distance could be obtained, which would enable fewer transmitters to cover more of a given area. Or two, to narrow the frequency bandwidth required for each radio signal, so that more frequency space would be available for additional stations. The engineers' efforts to accomplish one or the other of these objectives has resulted in a more efficient communications system. It's called single sideband, and it's described as a technique of selecting and transmitting only a portion of the frequencies of the conventional AM waveform. Now, before we continue with single sideband, let's take a look at AM. Let's summarize our knowledge of conventional amplitude modulation. Now, you know that in an AM transmission, an RF carrier is required, and that for 100% modulation, an audio frequency of equal peak amplitude is needed. When the two frequencies mix, the result is four frequencies: the two originals, the sum, and the difference frequencies, which are called the upper and lower sidebands. When modulating 100%, each sideband voltage is only half as great as the carrier voltage. The audio frequency is not developed in the output because the RF resonant circuits have a very low impedance to audio. The RF carrier and its sidebands are coupled through the RF tuned circuits to the antenna. So we transmit these three frequencies: the carrier, the upper and lower sidebands, in a composite waveform. Now let's review this composite waveform for just a moment. First, let's look at the frequency relationships. The carrier frequency determines the location in the spectrum of the transmitted signal. And when the carrier interacts with the audio, or the modulation frequency, the two sidebands are generated. Now, each sideband is spaced the distance of the audio frequency from the carrier. Now let's look at the power relationships. Each sideband voltage is only half as great as the carrier voltage at 100% modulation. In the formula for power, as you recall, P equaled E squared over R, voltage changes will square changes in power. So if each sideband voltage is only half as great as the carrier voltage, the power of each sideband must be only 1/4 that of carrier power, or 1/6 that of total power. Now, from what you have seen of the frequency and power relationships in the composite waveform, you know that varying the modulating frequency will vary the frequency of the sidebands. If the voltage of the modulating frequency is varied, the power in each sideband will vary accordingly. So you see that the two sidebands contain the same intelligence, but the power is equally distributed between the two. The carrier always remains constant in both frequency and amplitude. Now, if the carrier always remains constant, why does the oscilloscope show it varying in amplitude? Because what you see on a scope is not just the carrier, the sidebands are also present. To show the carrier by itself, while the sidebands were present, the display would have to look like this, showing all three frequencies in their individual forms and relationships simultaneously. But as you know, a scope cannot show three different voltage values simultaneously. It shows the instantaneous summation of these voltages. When all three are in phase, the resultant is large. When the sidebands are in phase with each other and out of phase with the carrier, the resultant is small. Thus you see what only appears to be the carrier varying in amplitude. But back to the composite waveform. Let's look at it in a little different way. We'll begin to see some undesirable things about the conventional AM signal. After the sidebands are generated, the carrier is not required for transmission of the sidebands. Now, since the carrier is constant in amplitude and in frequency, it contains absolutely no information at all. So why transmit it? Yet 2/3 of the total power is wasted in transmitting the carrier. Thus, the sidebands are being deprived of power which might increase the range of transmission. And also, since we have two sidebands, the required receiver bandwidth allows in more atmospheric noise at the received end. Noise, of course, is proportional to bandwidth. Thus, the wider bandwidth raises the noise level of the signal. If the signal is very weak, it may be lost in the noise and thus be totally unusable. Now, we have seen that identical intelligence is present in each of the sidebands. Now, since either sideband carries the same intelligence, transmitting both sidebands is a waste of frequency space. Since the carrier and one of the sidebands are not required for transmission, why don't we eliminate them and use their power to boost the remaining sideband? Well, let's see what would happen. We eliminate one sideband, we would narrow the required frequency spectrum by 1/2. And we'd still have the same intelligence in the remaining sideband. And by putting the power from the removed sideband into the remaining sideband, total sideband power is restored and is contained in just one of the sidebands. Well, so far, the sideband energy has only been rearranged with no resulting power gain in the information being transmitted. However, putting the carrier power into the remaining sideband would boost the sideband power tremendously. Now, all of the transmitter power is located in one sideband. Now, you recall that in conventional AM at 100% modulation, one sideband contains only 1/6 of the total transmitted power. Thus, if all the power were placed in one sideband, its level would be increased 6 times. This increases the power in this sideband by a factor of 6. But it only increases the intelligence power by 3, since part of the power was already intelligence power in the sideband that was removed. So by taking our conventional AM wave and just rearranging the power quantities through circuit changes, our transmitter is now effectively 3 times more powerful than before, using the same total transmitter power. Or to look at it another way, a single sideband transmitter requires only 1/3 the power to equal the performance of a conventional AM transmitter. Now, this is a tremendous advantage in itself, but let's look a little further. When we have 2 sidebands, the receiver bandwidth required is twice that needed for single sideband reception, giving us a lower signal-to-noise ratio. But now that we have eliminated one sideband, the receiver bandwidth may be narrowed considerably. And now what happens to the signal-to-noise ratio? The noise originally passed by the wider bandwidth has been reduced in the single sideband receiver. Now this means that with the same amount of received signal and only half the noise level, the signal-to-noise ratio has also been doubled. So our receiver has given us an effective gain of 2. This has increased the system's effectiveness by a factor of 6. Eliminating one sideband reduces the used frequency space by half. This increases the number of frequency channels available, and shifting the power of the carrier to the remaining sideband tripled the effective power of the transmitter. Reducing the bandwidth of the receiver doubled the signal-to-noise ratio, which effectively doubled the gain of the received signal. So a transmitter gain of 3, a receiver gain of 2, gives us an overall system gain of 6 over the conventional AM system. This is the theory of single sideband. Let's now compare it in an actual operating condition. Thus far, ideal transmitters, receivers, and propagation conditions have been assumed. When considering range versus power, the frequency of operation must also be considered. Extremely high frequencies are limited to line of sight regardless of power. Thus, increasing power above a certain level would not greatly increase the effective range beyond the line of sight transmission capability. In military applications, single sideband is normally operated at frequencies which allow long-range propagation by way of the ionosphere, which is radically different from the ideal conditions previously considered. Under average long-range propagation conditions, selective fading is likely to exist, and it is far more damaging to conventional AM signals than to the single sideband signal. Selective fading is caused by a combination of signals arriving at the receiver over 2 or more propagation paths of different lengths, resulting in phase distortion or cancellation of sideband information. Under conditions of extreme fading, single sideband communication has been accomplished when conventional AM systems of similar sideband power were completely out of service. So we see that the requirements of a single sideband transmitter must be elimination of the carrier, elimination of one sideband, and now let's take a look at the way this is done. Looking at the simplified block diagram of a conventional AM transmitter, let's change it to operate single sideband. Of course, we use a crystal oscillator of low frequency RF to generate a stable carrier. When we modulate it with an audio frequency, the two signals are mixed together in a balanced modulator, which is designed to cancel out the carrier and filter the modulating frequency in its output and produce only the two sidebands, the upper and the lower. We then insert a filter which will pass only one of the sidebands, and of course we can select either one, and we'll reject the other one. Thus we have only one sideband to be transmitted with all of the transmitter's power. At this point, if we desire to operate at a frequency other than the frequency of the sideband, we can change the sideband frequency by mixing it with another RF signal in a balanced mixer and selecting the sum frequency. We now have the sideband raised to a predetermined higher frequency containing the same recoverable data as the original. And by this method we can transmit a single sideband of any frequency with the full power of the transmitter. Now, let's make a quick comparison of this single sideband waveform with a conventional AM wave. As we have already shown you, this is the single sideband signal. Let's really appreciate the difference between the two by again looking at an AM wave. Here is an AM signal. When I'm not talking, you're looking at the RF carrier, wasted energy. When I speak, I modulate the carrier. The apparent changes in amplitude of the carrier are caused by the phase relationships of the sidebands generated. At this time, we're transmitting intelligence. But look at the wasted power in the carrier. Thus, the reason for single sideband. Only when we transmit intelligent information do we have a transmission. All of the power of the transmitter is directed to the intelligence. The bandwidth is much less. Therefore, the signal-to-noise ratio at the received end is higher. And of course, our transmitter efficiency is maximum. All of the transmitter power is delivered to the intelligence. This, then, is the big difference between single sideband and ordinary amplitude modulation. We have accomplished our purpose to transmit a single sideband signal, all of the transmitter power in the intelligence. But will a conventional receiver receive this different kind of signal? Let's look at a typical AM receiver and see. The incoming sideband signal is RF. Now, RF amplifiers, of course, will receive this signal and amplify it, and it can be mixed to produce an IF signal. The IF signal will be amplified as usual. But what happens at the detector? You recall what a detector does? It rectifies and filters the IF signal and detects the amplitude variations. But in a single sideband signal, modulated with a constant tone, the single sideband would have constant amplitude. The detector would rectify it, filter it, and out would come pure DC. No intelligence. So what must be done? Remember that the differences between the conventional AM and the single sideband waveforms were due to the absence of a radio frequency carrier. So if we insert an RF oscillator, let's call it a beat frequency oscillator, or BFO, to generate a constant frequency 1 kilohertz below the IF signal, like the original carrier, and mix it with the IF, the result is, of course, 4 frequencies. The IF, the BFO signal, an upper and lower sideband, or a constant carrier with sidebands of the audio difference. The resulting phase relationships restore the original envelope variations, and we can easily detect our audio. All we did was reverse the process of the transmitter. This is called reference frequency generation. The standard audio circuits will now select and amplify the audio signal or the audio amplitude variations, the original intelligence that we have transmitted. Thus, we have created a single sideband receiver. It can be readily seen that a single sideband receiver will be much more difficult to tune than a conventional AM receiver, and it must be, of course, very, very stable. The BFO must be precisely adjusted to simulate the removed carrier. Any drift at any time will cause the audio output to be distorted. So as we have seen, the obvious requirements of the single sideband receiver are reference frequency generation and excellent frequency stability. Now let's quickly summarize the entire single sideband system to make sure everything fits together. The transmitter generates a stable low-frequency RF carrier, which we modulate with an audio frequency. The balance modulator mixes the two and creates the sidebands. It also eliminates the carrier and the audio frequencies, passing on only the sideband frequencies. A sideband filter is designed that selects one sideband and rejects the other. In the balance mixer, the sideband is mixed with another RF signal to produce a sideband of a higher operating frequency. And the power amplifier amplifies and transmits this signal. A single sideband transmitter must accomplish carrier elimination and rejection of one sideband. The transmitted signal contains only one sideband with all of the power of the transmitter. This increases the effective transmission 3 times over an equivalent conventional AM transmitter. The reduced receiver bandwidth doubles the signal-to-noise ratio, resulting in an overall system gain of 6. It also decreases the required spectrum occupancy. This increases the number of stations that can now operate in the whole frequency spectrum. At the receiver, the sideband is processed through the standard RF amplifier, mixer, and IF stages, just as in a conventional AM receiver. The detector has been replaced by a BFO and a balanced mixer, which inserts a reference frequency to mix with the single sideband IF. This restores the AM wave shape, since the phase relationships now produce the original audio variations. And of course, the audio variations are selected and amplified by standard audio circuits. So the requirements of a single sideband receiver are reference frequency generation and excellent frequency stability. And that is single sideband in a nutshell. Now, we have seen that the characteristics of a single sideband system compared with the conventional AM system are more efficient use of available power, much greater reliability at long range under adverse conditions, narrower bandwidth and reference frequency generation in the receiver. We know our single sideband system has some disadvantages. We have seen that these are high frequency stability requirements, which of course means more complex circuits, which in turn may result in higher costs of equipment and maintenance. But let's compare the practical application of conventional AM and single sideband. For short-range communications for the general public, it would be impractical to have all of the public turn in their AM equipment for perhaps more expensive single sideband equipment, which might require more skill in tuning and higher maintenance costs. So conventional AM will be with us for quite some time in many applications. But for uses requiring long-range communications in ever-increasingly crowded frequency bands, the operational advantages of single-sideband far exceed its possible increased cost. Single-sideband is rapidly growing in use, especially in the military. So it's your job as an electronics technician to meet the challenge of both conventional, AM, and single-sideband.